Hello, and I am ThinkEasyScience. Yes, let's begin with relativity. But first of all, to understand relativity, you'll have to do one thing. Forget everything you know for just 10 to 20 minutes, and just focus on what I'm saying. This single video will clear all your concepts related to general and special relativity. The very first thing, broadly speaking, relativity answers 2 to 4 questions, such as, how is gravity generated? How does time run at different speeds for two people? For example, if you are in space and we are on Earth, our time will run at different speeds. As speed increases, distance decreases, meaning length contraction. Now, how do all these things happen? We'll understand all this in this video. Now look, relativity begins with an experiment, which was performed by many great minds, and that was measuring the speed of light. Now, you will ask me a question. Brother, was it then Nebik, break, and present tense Wandelhauer? One bit two tricky questions. Could the answer be contingent on one or two dimensions? And let's start with history. So, the matter is of 1633, the father of science, meaning Galileo Galilei. Yes, he is also called the father of modern science. An idea came to his mind. What would be the speed of this light? And just for the answer to this question, he gathered his disciples and, taking his equipment, went up a mountain. Now, his plan was that, brother, the simple formula for speed is distance upon time. Now, we will release light from one mountain, and his disciple, sitting on the other mountain, will note the time it took for the light to appear to him. And we have already measured the distance between the mountains. That's how the speed will be calculated. Now, as soon as Galileo operated his instruments and removed the shutter of the lantern, it was a blunder. The light instantly appeared, meaning it was as if the light took no time to go from one mountain to the other. Now, Galileo was very surprised. How could this be? What he couldn't understand was this. When the lantern was off, it meant there was no light. But as soon as the lid of the lantern was removed, the light must have taken some time to travel from one place to another. But in this experiment, it seemed like the light took no time, as if it were present everywhere, all the time. Now, the experiment failed, and Galileo said, "Come on, kids, we'll come back again tomorrow." But Galileo never came back to do his experiment because, brother, the church people caught him, and they asked, "Oh, scientist, where do you go every day? Now stay home and enjoy." Now you might be wondering what his mistake was. Brother, he had said that the earth revolves around the sun. The sun does not revolve around the earth. Just because of this, the church was displeased and confined him to his home. And with time, his chapter was over. After this, another great scientist enters, Olaus Rømer. Now, he said, if we have to measure the speed of light, we need to increase the distance. Now, an idea came to his mind. Why not solve this question with the help of Jupiter? I mean, the person was taking the distance up to Jupiter to measure the speed of light. Look at the level of the experiment. Now, this gentleman, by climbing around and setting up all the equipment on the roof, calculated the speed of light with the help of Jupiter's moon. But nobody trusted his calculation. So, brother, this scientist invited all those people who were in the opposition Bhajan Mandali group of critics to his house, and he told them that, brother, at a certain fixed time, Jupiter will have an eclipse. See for yourselves if you want. And that's what happened. Now, he became famous. And yes, I forgot to mention one piece of information. The speed of light that Olaus Rømer calculated was not the exact value, but it was quite close to it. This is why the speed of light was measured again and again later on. Now, as soon as the speed of light was determined, Christian Huygens started beating his drum, saying, "Got the wave, got the wave," meaning he declared light to be a wave. But just think, how did he know that light has a wave nature? I mean, he must have thought something. Just as other scientists performs different experimental programs, he must have also performed some kriya-karma, ritual. Sorry, what did I say? Kriya-karma? Sorry, a karyakram. Now, Christian Huygens said that when we throw a stone into water, waves travel in all four directions. And yes, that is absolutely right. Now, in exactly the same way, when a bulb is lit in a room, light travels in all four directions. And yes, this is also true. So if light is behaving like a wave, then obviously we will call light a wave. What else? Now look, in those days, this was a perfect logical explanation. Based on this, light was accepted as a wave. Now, a mischievous, clever scientist said, "Listen, Huygens Babu, I have a question. Just tell me, where are these light waves you are creating traveling on? I mean, a water wave travels on water. A sound wave travels in the air. So where is your light, that is, this light-named wave, wreaking havoc? I mean, in which medium is it traveling? Because a wave needs a medium." Now look, this was a very pertinent point. In response to this, Huygens said, "Look, brother, there must be some medium. Now, it's a different matter that we haven't found it yet. But what do we lose by naming it? Let's name it." And then it was named luminiferous ether, on which the wave of light, meaning the wave nature of light, propagates. Now both these events were from 1675, and now comes the time of 1704, and the uncle of physics, Chacha Newton, enters. Now, look, brother, Newton had already defined gravity, revealed the secrets of the solar system, and created the laws of motion. He was roaming around the scientific community like Thanos. No, I'm not kidding. At that time, Newton was such a powerful person that if he said something, scientists would blindly accept it without opposition. Now, upon arriving, he said that light follows the laws of geometry. That is, the angle of incidence is equal to the angle of reflection. And yes, that is absolutely right. But pay attention, this law of geometry applies only to straight lines. And yes, that is also correct. Now just think, if this law of geometry is only applying to straight lines, then waves are not straight at all. They move in a swaying manner. Now, this point also sounds absolutely correct. Then, Newton took a prism and broke the light into 7 colors. And he said, "Look, brother, light is made up of 7 rays that travel absolutely straight in a straight line. And waves don't travel straight. So these 7 rays are made up of particles of different colors, meaning corpuscles. And when these particles fall on our eye, we see things. That is, from today, light is a particle." Now, logically, Newton was absolutely right in his place, and from here, light got its particle nature. And Newton didn't stop here. He also made more assertions. He also said, time is absolute. That is, it can never change. It will run at the same speed everywhere, all the time. Now, one scientist opposed Newton. His name was Thomas Young, our own double-slit guy. Now he said, "Brother, light is not a particle. Uncle Newton left us with the wrong Churin, misleading idea, meaning light is a wave, not a particle." Now, the Newton supporters stood up in opposition to him. Then he said, "Brother, if we make 2 holes in a plate, meaning cut 2 long slits, and throw small particles through them, then only two lines will be formed on the screen placed behind this plate. That was absolutely correct. Then he said, if we place this same plate in water and let a wave pass through it, then the waves coming out of the holes will collide with each other and create an interference pattern. Meaning, it became clear to everyone that if light is passed through a double slit, if it is a particle, it will form two lines, and if it is a wave, it will create an interference pattern, meaning many black and white stripes. Now, as soon as this experiment was performed, the interference pattern was formed, meaning light was proven to be a wave. Newton was proven wrong. Now, if light is a wave, then brother, a wave needs a medium. What is the wave traveling on? So the debate came back to the same point. Find the medium, meaning find the luminiferous ether. Now, although later the Bayes law of physics, meaning our favorite Albert Einstein, later told us that, brother, light is a hypocrite. Dogly, light has a dual nature. Now, how and when this happened, I will tell later. Let's go according to the timeline of when which event happened. Now, listen further. After this, Armand Fizeau enters the story, and he calculates the speed of light again. But this time, the speed of light comes out almost exactly close to the exact value. The value that we still accept today, 3 lakh kilometers per second. Now look, many of the experiments I have told you in this video for measuring the speed of light, you can do at home. I won't teach you in this video. But if you want to know, tell me in the comments, and I will definitely make a separate video and teach you. And I will also tell you how these scientists got the idea to do these experiments and what they thought while creating their setup. It's not too difficult. And now the Michelson-Morley experiment enters the story. Now an idea came to Michelson and Morley's minds. And yes, Michelson and Morley are different people, whose full names are Albert A. Michelson and Edward W. Morley. They thought that if light requires a substance called ether to travel, then obviously our Earth is also revolving around the Sun. So our Earth must have some relative velocity with respect to this ether. Now they performed their experiment, and it was amazing. The thing they were looking for was not found, but they found out that there is no such thing as ether. And second, that the speed of light in a vacuum will never change. No matter what you do, light will always travel at the same speed. Now this was a very big thing, and from here, relativity begins. And now, the Bayes law of physics, the great scientist Albert Einstein, enters the story. First, let's understand where the idea of relativity came from in Albert Einstein's mind. Meaning, where did it start? So, brother, Albert Einstein was sitting and making hiali pulao, daydreaming. He was thinking that if someone says, brother, I am cycling faster than you, it means that one person compared his speed with the other person's speed. And the difference between the two speeds is the difference by which the faster cyclist is moving ahead compared to the other. A simple example must be understood. Now, just think that you are sitting in a car, and this car is constantly moving forward at a speed of 50 kilometers per hour. But how do you know that it is moving forward? It's a very straightforward thing. When you look outside the window, you will see things moving backwards. But if everything outside the window is removed, and there is no change in speed at all, then you will not be able to tell whether the car is even moving forward or not. Because then you will have nothing to relate to. What does this suggest? This suggests that speed is relative. Now, if speed is relative, then speed is made up of two things. Distance. Now we also know that distance is relative. But can time be relative? This was the question that was revolving in Albert Einstein's mind. Now, if time becomes relative, then Newton will be proven wrong. And if time remains absolute, then time will run at the same speed throughout the universe. Albert Einstein was looking for the answer to this thing. Albert Einstein knew that James Clerk Maxwell had stated that light is an electromagnetic radiation whose speed is 3 lakh kilometers per second. The second thing is that the speed of this electromagnetic wave cannot be increased nor decreased. This speed will remain the same in every condition, every circumstance. It will never change. It will also have no exception. Albert Einstein thought that if he and his friend race on bicycles, and the speed of both is exactly equal, then for each other, they will be at relative rest. That's absolutely correct. After this, Albert Einstein thought that if he races with light and somehow reaches the speed of light, he will get to see a stationary electromagnetic wave, because light is an electromagnetic radiation. Now, as soon as this thought came to Einstein's mind, brother, the roots of physics started shaking as the earth shook with the vow of Bhishma Pitama. And I am not over-exaggerating. You may not be able to understand the magnitude of this thought. What is the meaning of my words? Just listen to that. A single electromagnetic wave cannot be stationary, because if that happened, the laws of physics, electromagnetism, given by James Clerk Maxwell, would be torn apart. Everything related to electricity and magnetism in physics would be destroyed. But Albert Einstein also knew that these laws are absolutely correct. They cannot be wrong. Now, this meant that there was a flaw, a mistake, in the thought that Albert Einstein had created. So, this meant that Albert Einstein would never be able to achieve the speed of light. The point must be understood now why it is said that the speed of light cannot be reached. Now, from here, this point also became clear that one law of physics was stuck on saving its second law. That is, if the speed of light is achieved, a stationary electromagnetic wave will be found. But because the wave cannot be stationary, to save this law, light created a speed that can never be achieved. After this statement, Albert Einstein concluded that for light, the laws of physics are behaving differently, giving it special treatment, and looking at all other things differently. That is, the level of light is different. But Albert Einstein was not one to give up here. Now, he thought, okay, if I couldn't achieve the speed of light, no problem. Let's do something else. And he thought that, if the speed of light is fixed, and the laws of physics are also correct, then what will happen when light is emitted from moving and stationary objects? Because according to the laws of physics, the speed of light emitted from a moving object should increase. Understand with an example. If I am walking at a speed of 10 kilometers per hour, inside a train that is moving at a speed of 50 kilometers per hour in the direction of the train's movement, then the person standing outside will see my speed as 60 kilometers per hour. So, this thing should also happen with light. The speed of light coming out of a moving train should be faster than the actual speed of light, because the laws of physics told us this. But the same law of physics also said that the speed of light will never change. Here, two laws of physics have pointed a gun at each other. If one is considered correct, the other will be wrong. Now, which law am I talking about here? Pay attention to this. One law is of motion, meaning relative motion. But this law is not applying to light, because the Michelson-Morley experiment had proven that the speed of light cannot be changed. Now, if Newton is correct, the speed of light will be finished. And if the speed of light is correct, Newton's law will be finished. Now, the problem was how to prove both these laws correct simultaneously. So a remedy was found for this too. Listen. Albert Einstein knew that both these laws of physics are absolutely correct. But keeping both these laws happy at the same time was a difficult task, like pushing a mountain. Then he thought, why not sacrifice one more law of Newton? And that law was Uncle Newton's statement that time is absolute. That is, time is not absolute. It will depend on your and my perspective, on our frame of reference. That is, this means that time will be slower for the moving train. And by assuming this, the speed of light will be the same for both trains. And the two laws of physics, that is, Uncle Newton's law and the Michelson-Morley experiment's statement that the speed of light is fixed, can happily party together. Now, if time is different for two people, there must be some difference in it. Yes, absolutely there is. Let's find it. This is my light clock, in which a photon is bouncing up and down. My friend also has exactly such a clock. A photon is also bouncing up and down in it. I am moving with my clock, so my friend will see the path of the photon moving in my clock as something like this. Now, because from my friend's perspective, the photon is moving on a diagonal path. That is, the photon has covered a greater distance. So, it must have taken more time for this task. But if you talk from my perspective, the photon is still dancing up and down in my clock. That is, it must have taken the same time it should have taken. This is the distance covered by light from my perspective, c times t, and this is the distance covered by light from my friend's perspective, c times t prime, and this is the distance covered by the photon clock in horizontal motion, v times t prime. Let's rotate these crooked lines a bit. Let's see what happens. Oh my, this turned out to be the Pythagoras theorem. Celebrate, party, understand the work is done. Now, let's take a little help from maths. And after rotating and cutting/simplifying, we got the time dilation equation. See how easy it was. People made an unnecessary fuss about it. Einstein's special theory of relativity did not apply to accelerated motion, whereas in the real world, things accelerate. So, after 10 years, Fupaji, Einstein, gave us a new Turin called the general theory of relativity. Assume you jumped from the roof of a building. Don't jump. This is a thought experiment. So, as you come down, you will feel weightless. Wait a minute. This also happens in space. Without gravity, we also roll and tumble around there. We won't feel our weight there either. Now, imagine another situation. Let's say, on Earth, you weighed yourself by standing on a weighing machine. For example, your weight came out to be 80 kilograms. Assume this same room is accelerated upwards at a rate of 9.8 meters per second squared, meaning equal to Earth's gravity. And then you are made to stand on that weighing machine. Your weight will come out the same as it was on the surface of the Earth. And if that is the case, how will you differentiate while sitting in that room, whether you are on the surface of the Earth or in space? Yes, you can't. No one can differentiate. Something very strange happens with light in such circumstances. If I release a photon from one corner to the other in the same room, it will hit the wall slightly below its exact location. Because due to the room accelerating upwards, the opposite wall will shift slightly upwards. And if I trace the path of the photon, this path will appear to be bent. Look, light will bend, and this has been experimentally proven. So now it's time to explain this. So, Let's explain it. Listen carefully. This is our dear house on our dear Earth. Now, let's also place a scale in it, so that the length from the floor to the roof of the room can be calculated. Now, placing a torch in it, let's release a photon, and let's trace its path, which will be absolutely straight. But as soon as we take this room into space and accelerate it at a rate of 9.8 meters per second squared, meaning giving it the same acceleration as the gravity on Earth, there will be no change in the environment inside the room, because acceleration is equal to gravity. We already know this. Now, as soon as the photon comes out of the light, it will hit the